In the quiet skies above America, a shadow moves undetected. It's one of the most advanced aircraft ever built, the B-2 Spirit, better known as the stealth bomber. With a wingspan wider than a football field, yet almost invisible to radar, this aircraft is both a marvel of modern engineering and a symbol of unmatched strategic power. But how is such a legendary machine created? Today, we're going behind the scenes, inside some of the most secure facilities on Earth. We're up to uncover the extraordinary process of designing, building, and testing the B-2 stealth bomber. The story of the B-2 begins in the 1970s, during the Cold War. The United States needed an aircraft capable of penetrating deep into enemy territory, without being detected. Engineers and scientists turned to a revolutionary concept: stealth technology. This meant designing an aircraft that didn't reflect radar waves the way normal planes do. Instead of sharp tails and vertical fins, the B-2 was given a sleek flying wing design, a continuous, smooth surface that scattered radar signals. The design wasn't just futuristic, it was nearly invisible to enemy tracking systems. At Northrop Grumman's top-secret facilities, thousands of hours of computer simulations were run. Engineers tested how different shapes reflected radar. Even the smallest curve could mean the difference between detection and invisibility. By the early 1980s, the concept was ready to leave the drawing board and become a reality. The B-2 isn't made from ordinary aluminum. To achieve stealth, its skin required advanced composite materials. The outer layers use radar-absorbing materials, often referred to as RAM coatings. These special polymers and carbon fiber composites soak up radar waves instead of bouncing them back. Underneath, the main structure uses titanium and high-strength carbon composites. Titanium provides durability and resistance to heat, while composites keep the plane lightweight, essential for long-range missions. Every rivet, every panel, even the paint had to be carefully engineered. A standard glossy finish would reflect radar, so the B-2's matte gray coating helps it blend seamlessly with both sky and ground, depending on altitude. The construction of a B-2 starts with its massive wing frame. Unlike traditional planes with a fuselage and wings, the B-2 is one continuous flying wing. This requires building gigantic molds and precision tooling machines. Sections of the wing are layered with carbon fiber sheets, then placed in enormous autoclaves, giant pressurized ovens that bake the composites at high temperatures. This process bonds the materials together, creating panels strong enough to endure the stresses of supersonic flight, yet light enough to conserve fuel. Robotic systems ensure perfect alignment, while human technicians check tolerances measured in fractions of a millimeter. Any imperfection could compromise stealth or flight safety. Once the airframe is complete, engineers begin installing the B-2's intricate internal systems. First come the fuel tanks, built directly into the wing structure. The B-2 can carry over 20,000 gallons of fuel, allowing it to fly more than 6,000 nautical miles without refueling. Next, 4 General Electric F-118 turbofan engines are carefully mounted inside the wing. Unlike most jets, their exhaust nozzles are recessed, designed to minimize infrared heat signatures. This reduces the chance of being tracked by heat-seeking missiles. Then comes the electrical wiring, more than 60 miles of cables, all routed through narrow conduits. These control everything from navigation to weapons release. Advanced fly-by-wire systems replace traditional mechanical controls. Instead of cables and pulleys, computers interpret pilot inputs and adjust the aircraft's control surfaces automatically. Without computers, a flying wing like the B-2 would be nearly impossible to control. One of the most secretive steps in building a B-2 is applying its stealth coating. Specialized teams apply multiple layers of radar-absorbing paint and materials by hand, using techniques still classified to this day. These coatings must be perfectly smooth. Even a tiny chip or crack could reflect radar and reveal the aircraft's position. Maintenance crews later spend countless hours inspecting and repairing these coatings to ensure maximum stealth. In addition to the coating, the B-2's air intakes are carefully designed with serrated edges that scatter radar waves, while the cockpit glass is coated with thin metallic films to block radar reflections from the instruments inside. The B-2 is designed not just to fly undetected, but to deliver devastating payloads with precision. Inside its internal bomb bays, it can carry up to 40,000 pounds of weapons, from conventional bombs to nuclear payloads. The choice to place all weapons inside the fuselage is crucial. External pylons would ruin its stealth profile. Advanced racks and release systems are installed, allowing the B-2 to deploy weapons with pinpoint accuracy while remaining invisible on radar. The B-2's brain lies in its avionics suite, one of the most advanced in the world. Its navigation systems allow it to fly thousands of miles with GPS precision, even without external communication. This ensures the bomber can reach its target undetected, regardless of weather or terrain. The cockpit is equipped with digital displays, giving pilots real-time data. But unlike commercial jets, the B-2 requires two pilots, one to handle the complex navigation and one to focus on mission systems. State-of-the-art defensive avionics constantly monitor the environment. If an enemy radar locks on, the B-2's systems analyze the signal, identify the threat, and recommend evasive maneuvers, all in seconds. Before a B-2 ever leaves the factory, it undergoes rigorous testing. Every control surface is checked for movement. Engines are run on the ground, measuring thrust, fuel consumption, and noise levels. Special anechoic chambers test its radar cross-section. Engineers fire radar signals at the aircraft to ensure it remains virtually invisible. Then comes the first flight. Test pilots, highly trained and sworn to secrecy, take the B-2 into the skies for the first time. They push it through extreme maneuvers, testing speed, altitude, and stealth. Only after passing hundreds of hours of evaluations is the B-2 cleared for operational service. Once delivered, the B-2 is based at Whiteman Air Force Base in Missouri, the only location in the world where it operates. From here, it can strike anywhere on the globe within hours. With aerial refueling, its range is virtually unlimited. Pilots undergo years of training to master the B-2. Flying such an advanced aircraft requires precision, discipline, and trust in the technology. When on a mission, the bomber cruises high above enemy radar, undetected, until it silently releases its payload with pinpoint accuracy. The B-2 stealth bomber remains one of the most expensive aircraft ever built, with each unit costing over $2 billion. Only 21 were ever produced, making it one of the rarest aircraft in history. Even today, decades after its first flight in 1989, the B-2 is still considered a cornerstone of U.S. air power. Its legacy paved the way for the next generation of stealth technology, including the upcoming B-21 Raider. But for now, the B-2 Spirit continues to serve, a silent guardian in the skies, its secrets hidden in shadow. If you enjoyed this deep look inside the making of the legendary B-2 stealth bomber, don't forget to hit subscribe and turn on the notification bell. Here, we uncover the hidden stories behind the world's most incredible machines, from the factory floor to the skies above. Join us for more episodes of How It's Made, and be the first to explore the technology, craftsmanship, and secrets that shape our world. Click subscribe now, and let's keep discovering together. Every day, tens of thousands of flights take to the skies around the world, connecting people, economies, and cultures. At the heart of this global web of air travel stands one of the most iconic aircraft ever built, the Boeing 737 MAX. With its sleek design, advanced technology, and promise of fuel efficiency, the 737 MAX is more than just a plane. It's a symbol of modern aviation. But behind every smooth takeoff lies a story of precision engineering, rigorous testing, and a complex global supply chain that never sleeps. In this documentary, we go inside the world of the Boeing 737 MAX. From its conceptual design on digital blueprints to final assembly in Renton, Washington, from wind tunnel tests to its maiden flight, we'll explore every bolt, rivet, and circuit that goes into making this aircraft soar. Along the way, we'll uncover the triumphs, setbacks, and evolution of a jetliner that aims to redefine how the world flies. So buckle in as we uncover the story of the 737 MAX, a journey of ambition, innovation, and flight. The story of the Boeing 737 doesn't start with MAX. It begins in 1967, when the very first 737 took off. Designed to be a short-haul companion to Boeing's larger 707 and 727 jets, the original 737 was a narrow-body aircraft that would go on to become the best-selling commercial jetliner in history. With each generation, the Classic, the next generation, NG, and now the Max, Boeing engineers pushed the envelope further in fuel efficiency, passenger comfort, and digital innovation. But the road to the Max wasn't without turbulence. In response to Airbus's fuel-efficient A320neo, Boeing accelerated the development of a new iteration, the 737 MAX. With larger LEAP-1B engines, updated avionics, and aerodynamic improvements like split-tip winglets, the MAX promised a 14% improvement in fuel consumption over its predecessors. Launched in 2011 and first delivered in 2017, the MAX was poised to dominate the skies. But in 2018 and 2019, two tragic crashes involving the MAX 8 variant led to a global grounding of the fleet and intense scrutiny of Boeing's design and safety practices. The MCAS software system became a focal point in investigations and revealed flaws in oversight and communication. Boeing responded with comprehensive software updates, enhanced pilot training, and renewed transparency with regulators worldwide. After nearly 2 years on the ground, the 737 MAX was recertified and cleared to fly again. Today, it continues to rebuild trust while logging millions of safe flight hours with airlines across the globe. More than just an aircraft, the 737 MAX is a case study in resilience, of a company, of engineering, and of aviation itself. And understanding how it's built, tested, and operated reveals the immense effort behind each flight we often take for granted. Coming up next, how does Boeing source and transport thousands of parts from around the globe to one single assembly line? Welcome to the global supply chain behind the 737 MAX. Before a Boeing 737 MAX ever sees the runway, its story begins across a network that spans the globe. Unlike consumer products made in a single factory, a modern commercial jetliner is the result of a symphony of international suppliers, synchronized with industrial precision. In fact, more than 400 major suppliers contribute parts to the 737 MAX, each playing a vital role in delivering a machine capable of flight. The process begins with coordination. Boeing's supply chain team works with partners in over 50 countries, managing everything from fuselage panels to electronic avionics, from titanium bolts to engine pylons. The aircraft's primary fuselage sections, including the forward, mid, and aft bodies, are manufactured by Spirit Aerosystems in Wichita, Kansas. These massive sections, sometimes longer than a city bus, are shipped by rail or specially designed flatbed trailers to Boeing's final assembly facility in Renton, Washington. The wings, they're made in Japan. Mitsubishi Heavy Industries fabricates the wing structures using a combination of aluminum alloy and carbon fiber reinforced plastics. These are shipped across the Pacific Ocean to the port of Seattle, where they're carefully transferred to the Renton site. Meanwhile, the aircraft's most iconic upgrade, its LEAP-1B engines, come from CFM International, a joint venture between GE Aviation of the US and Safran Aircraft Engines of France. Each engine is a masterpiece of engineering, designed to be both powerful and efficient. Before installation, they are tested under simulated flight conditions, including extreme heat and cold, at facilities in Ohio and France. Every component, from the landing gear produced in Canada to the seating tracks from Germany, must meet Boeing's strict design tolerances and be delivered on a just-in-time basis. There is no room for error. A delay in one part could halt the entire assembly line. But it's not just about hardware. Embedded throughout the supply chain are systems for quality assurance, cybersecurity, and real-time tracking. RFID tags, barcode scanners, and cloud-based logistics platforms ensure that every bolt, wire harness, and circuit board is traceable, from origin to installation. And when the parts arrive at Renton, they're not stacked in warehouses. Instead, they are delivered directly to the workstation, where they'll be installed, often within hours. This is called a moving production line, and it's designed to minimize inventory, cut costs, and keep aircraft rolling steadily down the line. In this system, precision isn't optional. It's the only way forward. Boeing's global supply chain operates like a finely tuned orchestra, delivering thousands of high-stakes components on time, every time. And with demand for commercial aircraft projected to grow in the coming decades, the efficiency of this system will only become more critical. Next, we head inside the assembly plant in Renton. one of the most advanced aircraft production facilities in the world, where all these components finally come together to form a flying machine. Nestled along the shores of Lake Washington lies one of the most productive aircraft factories in the world, Boeing's Renton facility. While it may look like an ordinary industrial complex from the outside, inside, it's a marvel of modern engineering. The birthplace of every Boeing 737, including the 737 MAX. Unlike traditional factories where assembly is static, Renton operates on a moving assembly line. The aircraft physically travels from station to station along a massive production floor, an innovation modeled after the automotive industry. This approach allows Boeing to produce up to 42 jets per month, a rhythm that balances speed with surgical precision. The process begins when the fuselage, built in Kansas and transported cross-country by rail, arrives at the northern end of the line. This long, green, tube-like structure already has windows and basic internal systems installed. Once inside the factory, it's lifted onto special supports called tooling fixtures, which allow technicians to access the aircraft from every angle. Step by step, the airplane begins to take shape. First, technicians install wiring and avionics. Thousands of feet of insulated wire, for everything from lighting to flight controls, are routed through narrow conduits with meticulous care. Every connection is scanned and tested for continuity. This electrical nervous system will power everything from the cockpit to the coffee maker. Next comes wing installation. The massive wing structures, delivered from Japan, are aligned to millimeter-level precision and bolted to the fuselage using specialized torque tools. Technicians also install the aircraft's main landing gear, hydraulic lines, and fuel systems. Each component must be balanced, leak-tested, and pressure-checked before the build moves forward. Throughout the process, technicians work side by side with advanced robotics. These machines drill thousands of holes and insert rivets with incredible accuracy, faster and more consistently than human hands. Yet, crucial tasks like sealing, system integration, and inspection are still performed by skilled workers. This human-machine synergy is what makes Renton so efficient. As the aircraft glides down the line, it begins to resemble a complete airplane. Interior teams install insulation, floor panels, overhead bins, and seating structures. Meanwhile, the flight deck is outfitted with control yokes, instrument panels, and touchscreen displays, all designed to reduce pilot workload and enhance situational awareness. Finally, the LEAP-1B engines are mounted beneath the wings. These are the heart of the 737 MAX, quiet, powerful, and fuel-efficient. Once attached, every system is connected, tested, and validated. Teams run diagnostics on avionics, hydraulics, environmental controls, and more. Nothing is left to chance. At the end of the line, the aircraft receives its final paint job, often in the livery of a specific airline customer. It's then towed out of the factory to the adjacent flight line, where it will undergo functional tests, fueling, and, most importantly, flight testing. What began as a scattered collection of parts from around the world is now a fully functional aircraft, ready to defy gravity. But before it can carry passengers, the 737 MAX must prove itself in the air. In the next chapter, we follow the jet as it undergoes rigorous testing, inspections, and certification, the final gate before it can earn its wings. A commercial airliner is among the most rigorously tested machines ever built, and for the Boeing 737 MAX, that scrutiny is even more intense. Before a single passenger steps on board, each aircraft must pass a gauntlet of inspections, diagnostics, and flight evaluations designed to push its systems to the limit. Once final assembly is complete, the aircraft rolls onto what's called the flight line, an area adjacent to the Renton plant where it undergoes its first real-world tests. Technicians begin by powering up the aircraft for the first time. This is a critical milestone. Dozens of independent systems, electrical, hydraulic, pneumatic, environmental, must boot up in perfect sync. Any discrepancy triggers immediate troubleshooting. Next, the aircraft is fueled for the first time, not just to test engine startup, but also to verify that fuel tanks, valves, and sensors work flawlessly.